All right, welcome back. We are game 3001 in the summer 2021 semester, and it's week 5, part 1 of our broadcast. And today we're talking about a couple new things. So division schemes, we're going to talk about that a little bit, and something called path smoothing. And we'll talk about how that can help us when it comes to doing pathfinding. So let's get into this. So again, what we did last week was we really talked about graphs. What are they? We talked about things like, directed, non-directed graphs, weighted graphs, what nodes are in graphs, as well as what connections are. We talked about that briefly last week. We also kind of described Dijkstra's algorithm last week. It's also called something called a uniform cost search, that's what it does. It kind of looks at every node in a uniform or the same way, right? So it does almost like a cost so far, and it doesn't use what A-star uses, which is a heuristic, which is kind of an approximation or an estimation on how far the goal is from the start of your pathfinding, right? So that's one thing it doesn't do. But what it does do, Dijkstra's explores lowest cost paths as a priority and then selects the shortest path. So it's a little better than, let's say, breadth first search. There's other search algorithms out there as well. But it wastes some time exploring in directions that aren't really promising. So it kind of goes and explores other directions as well. A-star is a little bit more, I'm not going to say efficient, it's just quicker in some ways, right? It computes, the kind of I would say the search function like this. It takes the cost so far, right? And then it adds on the heuristic. So that's what this F is equal to G plus H, where G is the cost so far and H is the heuristic function. All right, so it kind of adds those two together to give you the the best search that it's going to do. That's what it kind of does for every connection. It's faster than Dijkstra. We talked about this, and it selects nodes based on the heuristic. It prioritizes paths that seem to be leading closer to a goal. So if it's like, for example, let's say we have a goal at one part of the screen, then it's going to prioritize the paths that kind of get us closer to that goal. And that's a different way of doing things than, let's say, exploring just the lowest cost paths, right? So it's a little bit more almost like forward thinking in some ways. It can return a less optimal path though, because it's going to try and find the, the path that leads closer to the goal, and but may not explore all paths. Whereas Dijkstra's will explore kind of more paths than maybe A-star, and breadth first search other paths as well. Other kind of algorithms will search in a different way. So those are the kind of algorithms we explored last week. And then during the lab, we created a tile and grid system, and we stacked the game objects to the grid. We talked about how to do that with GUI. And in the video, I didn't quite get to it in the first lab, but in the second lab, I did it with the video. And we're going to do our second lab based on this week's lab based on the second lab from last week. All right, so where we're sitting at week 5. This week we're talking about path smoothing and a little bit more about division schemes, like we said. Next week, just to kind of look forward, assignment 2 is due, so let's keep that in mind. Remember that for assignment 2, one thing to note is you need to join a group. Some people have sent me messages saying, I can't see the assignment. I don't see the assignment 2. You'll never see the assignment 2, guys, unless you join a group. So please do that. I keep saying this week over week, sign up for groups. If you don't sign up for groups, as an example, then you won't see the assignment. And if you don't see the assignment, you can't submit, right? So that's kind of pretty straightforward there. So please make sure you do that. Lab 5 again this week is due on Sunday, as an example, and then again, assignment 2 is due next week on Sunday. And we're not so far off we're only a couple weeks away from doing our midterm test, which is going to be a multiple choice true false type test that's going to happen during week 7. And then there's a mid-semester break, and then you're into decision making, which is, again, way more challenging than what we're doing so far. Okay, so that's kind of what's happening. Next week, I'll also release assignment 3, so you can start working on it for those people who want to. I recommend you get going on it and create groups. There'll be different groups for assignment 3. than assignment 2. So it'll allow you to kind of connect with other people. Let's say, for example, you didn't quite like your team member from assignment 2. Well, that's okay, because assignment 3, you'll have a chance to switch it up, and it'll be the same thing for assignment 4. So I'll make a couple of new group sets for assignment 3, group sets for assignment 4, and then it should be fairly straightforward for you. Andre says, how the tile manager works. How you draw the tiles. Okay, we'll get into that. Ask me again during lab, Andre, but more or less what we're doing in when we draw tiles is we're actually, creating a grid, and the grid is going to be based on a tile size. So for example, we chose a tile size of 40 by 40 pixels, and then we're drawing it using the draw function that I've kind of created for you. That is just actually part of the SDL draw functions. We're not loading anything. There's no actual texture that's being drawn. It's kind of creating a texture in real time for each of the tiles. So what it does is it just draws everything. But one thing we didn't do last week is we didn't make any relationships between one tile and its neighbor tiles. And we're going to do that this week. This week, we're going to kind of do more in terms of how to create a relationship or understand each of the neighbor tiles. What are they? And that kind of stuff. So we draw the texture tile.png. No, we don't use tile.png at all, actually. We draw a rectangle using the SDL. So the SDL draw tools. That's all we're doing every frame. And for each tile, and that's what we're doing. That's how we draw everything. So we don't use a texture at all in this case. All right, so that's we'll get into that again during lab. So that is kind of what we did last week, and what's coming up for next week and the week after. So again, if you haven't had a chance to start assignment 2, get moving. I would recommend move on it as soon as possible. There's a lot more details in assignment 2 than in assignment 1. Remember, in assignment 2, you also are required to create and I'm going to put it in kind of air quotes here, an interesting map, right? And people have asked me that question, what's an interesting map? It means that I don't just want to see the tiles in grid form. You'll lose marks if you just do that. An interesting map means you have to make it so that there is some kind of tile map, or you can draw something out. And the back end, invisible to the user, you're going to have a tile and grid system. But on the front end, you won't have a tile and grid system. It'll look like it's just a map that your your vehicle, your avatar, whatever it's going to be, your autonomous character is going to navigate through, around obstacles and those kind of things. So that is what you're going to be doing. So please get going on that. You can start getting those assets now. You don't have to wait for all the examples we're going to do in class. Okay. So I kind of urge you to get started. I think there's a lot to do, and there's never enough time to do this stuff. Don't leave it to the last minute. This is an assignment you can't really do that with. So get moving on it as soon as possible. All right, let's do a couple of things in review. What I've also done for you guys is up on. I'm just going to. Just do a couple of things here. One sec here while I do that. I want to make sure that it is serious. I've been marking also, one thing also I have to mention is that I've been marking your assignments for assignment 1. I'm about 30% done, I would say at this point. I'm going to get the rest done today, so you should have some feedback for your assignment number 1. Things I've noticed for the assignments that I've marked so far, there are issues when it comes to you guys following directions. Some people just don't do what I've asked them to do. They don't have some people didn't have a start scene at all. No start scene, or if you don't show me a demonstrated start scene, then you get 0 marks for that. Remember that I'm using a rubric, but the rubric is just basically, just a way of giving you or gamifying your results. So I'm still using the same kind of details that I've given you in the assignment. So if you're missing something, and if it shows you a mark that's less than 100% in each part, it's because you've missed something, or you could have done something different from a coding perspective And that's why you got less marks. If you didn't submit something, let's say, for example, you didn't do obstacle avoidance, and there's quite a few of you who didn't, you'll get a 0 for that piece, but the rest you'll get marked for, right? So please work on those things. Some people also didn't do things like submit sounds at all. They like literally didn't read through things, or they just did, I don't know, they didn't do it, right? So for the things that you didn't do, you'll lose marks, right? As an example. So that's something that I have to mention as well. Let's get into a couple of these links. I wanted to share with these because these can help you, again, visualize some stuff that we talked about from last week, so to help you with your assignment. So here's an introduction to A-Star from Amit's Thoughts on Pathfinding. This is from Stanford University. So this guy really talks about how the algorithm works. And he goes through and describes Dijkstra's algorithm in kind of graphic detail, as well as what it looks like and some common problems like the room problem, how it kind of works out that problem, and depending on if you have a different kind of search, a greedy best first search, as an example, as opposed to a Dijkstra's algorithm. And then A-Star and what that looks like compared to something like, so notice like A-Star will actually kind of explore this area, but then we'll find the shortest path this way, right? So it'll kind of backtrack. So what happens is A-Star kind of, explores this part of the grid and then backtracks and finds the shortest path this way. So that's what it does. There is a bit of backtracking for every algorithm. And take a look at this one. This is your, your Dijkstra, right? Or your best first search. This is, kind of one and the other. It kind of describes different ways. And here's the fill pattern that it makes before it finds the, kind of the shortest path. So that's the kind of thing that you want to look at to kind of explore what the fill pattern, quote unquote, is as an example. And you can see the difference between the three different algorithms that it explores here. He also talks about heuristics, and he's got a lot of other pages here. So I've included this for you as something you want to read on the side. He also talks about some pseudocode and stuff like that as well. So really a pretty good research, kind of a reference, if you will, for something that I recommend. And it's fairly detailed. I think he talks about a lot of different things. It's good to know about this stuff. So that's that one. The other thing is there is a little video that is shown. And again, even though I'm doing a little video, I can reference this one. He really talks about creating a randomized kind of grid. Kevin Wang here. This is what he talks about. And he goes into detail about, again, fill patterns. Here's A-Star compared to Dijkstra. So this is kind of good. And you can see the difference between one algorithm and the other. One thing to note is it doesn't mean just because, like we said before, that A-Star is quicker, that it's better necessarily in terms of, or the shortest path. One also thing to note is in his examples, he can change your grid size and stuff like that as well. Now, the great thing, why am I showing you this? It's nice to watch, but the one thing that he has also is he kind of shares kind of the his Git repository, and Git repository is written in Java, but it doesn't matter because you can still take a look at somebody else's code like this and then see what they did in terms of, kind of their, their solution. So if you look at where it says demo, as an example, you can look at the model where it talks about the A-Star pathfinding algorithm, right, as an example. And yeah, let's do that. And then we can kind of look through this, and you can see that he talks about how to put things together, with his little pseudocode. So you can look at some other people's code, and maybe it might help you when it comes to putting together your stuff for assignment 2. So that's what I've given you a couple of examples. I think it's interesting to look at something like this from a video perspective to see how the fill pattern works. And then when you do your own, you can kind of say, well, how does mine look compared to what I've seen online? I think this is good as a reference. Okay, so that's kind of a couple things that I wanted to share with you today before we move into our topic. Don't worry, I took care of that, Efrain. All right, so that is where we're sitting. So today what I want to talk about is this idea of a navigation graph and what that is, right? So again, what we want to do with pathfinding is really determine the path from A to B using some kind of search algorithm. And what we want to start thinking about is how do we partition the game environment? Okay, so we need to create some kind of data structure to do that. So again, there's a lot of different ways and different kind of geometry in the game world. Sometimes we use the tile, a node, or some kind of polygon-based, kind of structure. There's a lot of different ways of, splitting up the game world. So let's examine a few methods. I think is a way to start. So here's one: a tile or a cell-based kind of navigation scheme. And in those kind of games, we have a tile-based game. Typically we use them for, a real-time strategy game or other kind of turn-based strategy games. They use either squares or hexes, and we've seen those before. For example, in things like Civilization or even things like Catan, as an example. They have some kind of hex or grid system. By the way, the early versions of Civilization use squares, and then they move to hexagons, right, which is kind of interesting. And it's a different kind of navigation than square tiles. It provides different ways of moving across. And in fact, in many strategy games, even in desktop strategy games, we use hexagons because they provide different ways of moving in diagonal formations. So we can think about then, when we have our game world, how do we divide our game world? And in this case, when we think about a navigation graph for a cell and or tile and grid system, each graph node is the center of the cell, and with the graph edges are the connections between adjacent cells. So you can't see the adjacent cell necessarily, right, or the connections, but we can imagine that there's going to be a connection from the middle of each node, if you will, to each other node. Okay, so that's how it works. So usually there's some kind of cost, again, for maneuvering, okay? And that's one thing we haven't really talked about. For example, if I turn left and right, excuse me, if I need to turn left and right to avoid an obstacle, there is a movement cost or a turning cost, if you will. So if I'm going in a direction, remember one of the things that I've asked you to do for assignment 2 is you're going to move in the direction that you're looking, right? So you could assign, if you really wanted to, in your game, a turn cost. So if I turn to the right or to the left, then I increase the amount of energy it takes. And that could be the total path cost. Energy cost could be related to your path, okay? So here's an example of things. We really haven't talked about different kinds of terrain too much. We said that for now, all terrain costs for our grid is worth 1, the same, right? But you could definitely change things. You can have either water or mud or something different for if you're creating a tank game that have different path costs. So for example, from going from one location to the other, some paths are going to be expensive because they're just going to be, you're going to be going through different terrain, right? So that's the kind of stuff that you can incorporate into your division scheme as well, where when you have, when you're designing a map, right, you can actually look at it and go, okay, so I'm making an interesting map for assignment 2. Well, okay, I'm adding this area that is more of a dangerous terrain or difficult terrain. So I'm going to increase the path cost for that particular part of the grid, all right, as an example. And it's interesting. You can definitely do it beforehand, and we can also talk about how to do things procedurally, which is something that I'm going to be doing with you guys probably during this lab or next lab. So how do we make a procedurally generated or randomly generated grid, and do we actually have a map to get to, as an example? So let's talk about this one. So really the downside, let's talk about tile-based navigation. Downside to using cells as the skeleton for a nav graph is that the search spaces can quickly become extremely large. So what that means is it increases the amount of nodes that we're going to use. So one thing I've asked you to do, because I'm asking you to use a tile and grid system, is the amount of memory that's required for a tile and grid system is much higher, as an example, than it is for a kind of an open navigation like node and connection. kind of grid system. That's a totally different way of doing things. So one thing to notice, like for example, 100 by 100 cell map, and in our case, it's not quite that large. Ours is a 25 by 15 kind of cell map, but for something like 100 by 100, you have 10,000 nodes and 78,000 edges for 100 by 100, and that doesn't include. You have to keep track of all this stuff in memory, right? So there's a lot of number crunching involved, when it comes to using a tile and grid-based system. Another way of doing it is using something called a points of visibility graph. So this is another data structure that we can use. And what you're doing is you place graph nodes, usually by hand, at important points in the environment. So you're actually mapping it, a little bit more granularly than using a tile and grid system. And so what's happening is you have to make sure that from each node to the other node, you have a line of sight. And what this really does is it allows you to move around the geometry in a different way. Here's an example of a lines or points of visibility. So from one point to the other point, from each node to the other node, you have line of sight. Okay, so there's no obstacle that's blocking your way. This is an interesting idea as well. And again, a different kind of division scheme where you have less nodes, way less nodes than the other ones. And however, what ends up happening is you have less choices for the AI as well. So one thing, when you have the smaller number of nodes, then this, the smaller number of choices, which means you're going to see the AI travel in the same patterns over and over again. And this is good from a programming perspective, but bad because it's predictable. Because I know that the AI is going to go through the doorway in this particular exact point and come out this way, and then I can trap the AI at different places or predict what their pattern is going to be, and so on. So typically, you'd have more points of visibility on a map than this, because you need to make it at least 2 or 3 times more complex than this, and perhaps other different search paths, as an example, that you can use, right? And you can assign weights to these paths as well, based on kind of the terrain that's in these rooms. Okay, so for example, if you're in an enclosed area like this, or some kind of sandbox, okay, this could be outside as well, right? So these walls or buildings or something like that, or debris, as an example, then that's okay, but you can create different terrain in here as well. So that's another way of making the map a little bit more complex and interesting. So again, so positives, so pros, they're easily expanded. So I can include, different nodes that offer information, about connectivity. So, as an example, I can add nodes to a map, and every time I add a good node, I can add nodes for things like good sniping and cover or ambush. So on that map that I just showed you, I can add additional nodes for the AI, and I can create different points of interest so that the AI will have, more opportunities to seem that they're more random. Downside is if the game map is really large and complex, the map designer can spend a whole lot of time going through and positioning and tweaking the graph over and over again. So that is kind of the next, kind of the negative thing. And it's also problematic if you plan to include some kind of map generation or procedurally generated maps, because basically what you have to do is when you create nodes, you have to make sure that they have line of sight to the previous node, as an example, and there must be line of sight to the next node. So what ends up happening is your generation algorithm will be much more complex in some ways because of this. I mean, again, it doesn't mean that you can't do it. It just means there's going to be more thought into creating a procedural map if you're using points of visibility as one of your division schemes. Okay. So that's something. World representation is also something we have to think about. So I need to take my entire world somehow, the way you've done it. Let's say, for example, in your game production game that you're making this semester with Philip, as an example. And when you look at your game world, how do I take the game world, that game world that you're making, whether it's you're making some kind of game which is, as an example, some kind of platformer, or you're doing some game which is like a tank type game, or whatever type game that you've been allowed to make this semester. So you take, your game. How do I translate that into nodes and connections? How do I do that, right? As an example. So again, we could divide the game into linked regions with some kind of division scheme, okay? And division schemes, when we think about division schemes, we think about these three things: quantization or localization, which is really how locations in the game level are converted into graph nodes. So I take, for example, some kind of mountain node or mountain area. How do I convert that into, an area that, a location that my AI can wander around? How do I do that, or patrol, right? Generation, how I can divide some kind of continuous space into regions and connections for pathfinding. Okay, that's one thing. So there's quantization, so I can convert it into graph, and how do I make it so that there's pathfinding involved? And the last one, which is actually important piece, is validity, right? Is there a way that I can make it valid? And one of the things we have a problem with when it comes to things like procedurally generating, again, when you think about this idea of procedural anything, you can replace a lot of times procedural, especially in the beginning, with random generation. How do I make a map that's randomly generated with pseudo-random numbers? How do I make it so that it's viable? And a good example of that is if I'm making, kind of like a system of tunnels or a system of connections from one room to another. How do I make it so that it makes sense, as an example, as opposed to, true randomness that has there is no path, as an example, from A to B. That's another thing. You have to kind of do another pass to make sure that there's a path when we do any kind of procedural generation. We'll talk about that maybe later as well. So here we go. There's a couple of problems here, right, where I have a start node and an end node, right? And you can see that here we have a corner, right? And this corner node or this corner obstacle could cause an issue with collisions, where you might have a problem where as the autonomous character moves from point A to point B, they get caught in the corner, right? They have a problem here. So this is like kind of a corner trap. The other one is what happens when, well, here appears to be closer from an A-star pathfinding than up here, so it takes this route and now there's this obstacle and it doesn't have any foresight, and we're going to be trapped in this area here. And the AI is going to get trapped in here, and then your character is going to come in and kill them. So that can happen as well. So one of the things that we can do is combine some of these scenarios. And I kind of say it ahead of time, and it's kind of spoilers, but what you could do is also use line of sight, right? So, the thing that I can also ask always is, can I see the goal? Can I see the goal? No. If my line of sight extends, and if my line of sight is pointing at an obstacle, right? Is this the right way? Should I ignore the way through this area if my line of sight is pointing at an obstacle, then turn until I don't have an obstacle? So that could be some way of doing it too. So example, if I'm in this room, and I'm just going to draw this through the annotation this time around. So so then I don't make a frame mad with, my way of doing things. So let's say, for example, do I have a line of sight between this way and that way, right? No, the answer is no. So then I'm going to turn, and how about this way? If I was facing this way or this way, I don't have a line of sight here, right? As an example. And the same thing goes with this guy, right? This one doesn't have line of sight. So if I'm here at different points, like, do I have line of sight here? As an example, do I have line of sight where I'm looking? No, the answer is no. And I want to keep turning until I do have line of sight. That's also a way of doing things with, converting. Remember what quantization is: converting your area into, nodes that are viable, right? So again, splitting this, some kind of division scheme, creating a division scheme that allows my AI to travel from one place to the other, and be careful about these kind of traps. These are traps that can occur, right? That we don't want to allow to happen. All right, so And let's go look at this one. So here's other issues. So this is valid partial blockage, right? And this is invalid partial blockage. Like if you had this, if you were making something like this, think about this corner. Corners are always a real challenge, right? So again, we still use grids as an example because grids can be turned into these tile-based graphs. And that's the idea behind them. But we have these issues, right? Where, you know, if I'm going from one grid to another grid, right? Well, here I don't have any problems moving. But if I had a larger object, I would hit the corner. That's the issue with this, right? So if I'm moving from one place to the other, this is okay, but this is not okay, right? And so this creates issues with, you know, kind of subdividing or, you know, creating a division scheme for my game world, okay? When it comes to tile graphs, there are, you know, we have a blocky way of moving, right? So if you look at the black path here, this blocky way of moving is, you know, one thing that we're going to do, especially when we're moving in the direction that we want to go. So let me annotate this again with red. So again, if I'm starting here, you know, and if I want to go to this place right here, as an example, how do I get to that position? Well, I can't see at any point in time from where I am right now, I can't see the target, right? So that's one thing that the, you know, that we're going to have. We can't see the target. So I'm going to have to use some kind of pathfinding thing. So I start off, and depending on how I do the pathfinding, whether I use A-star or whatever algorithm, it doesn't matter, right? It's going to lead me to the next best, you know, path location, right? So typically it's going to go this way. It's going to go be very blocky in the way it moves, like across this way. And this is going to be kind of wasteful and or not optimal in terms of the way it moves. So this is the first possible path, right? And with path smoothing, we can look at it and go, okay, yes, it makes sense that I would move this way because I'm inside of you know, of a grid system. And by the way, for our grid system, we can't even do this, right? Our grid system, you know, as an example, would even move worse than this. It would kind of do here, and then from here, it would go here, and then from here, it would go there, because we can only move up, down, you know, kind of right and left, you know. So from here, you may want to go, you might take us up to there, and from here to there, you know. So ours is even worse because we don't actually go through this thing. So what we want to do, the ideal direction is, if I'm going to go from here to here, here's a turn, right? Here's a turn. So if you think about this, we can start thinking about this as a pivot, right? Like we talked about this last time in lab a little bit. But if you think about this, right? Oops, let's try that again. So yeah, so we can think about this as a pivot, you know, as an example. Here's a pivot, right? Here's a pivot. This is where we're actually turning, right? And then here's a pivot, right? Is there maybe a way of getting from where we start to the pivot location, right? We're going to travel. This is the actual path, right, that we're going to travel. But is there a way of getting from here to there? Once we've established a path, before we start moving our character, can I see any of the pivot points? Can I see any of the pivot points, right? So if you think about this, right, and we start thinking about the path, one path smoothing algorithm could be something that looks like this. Well, do I see this pivot point? Yes. Do I see this pivot point? So I see this one. Do I see this one? Kind of, but I'm behind this area here. I'm kind of got maybe a blockage, or I have to go diagonal this way. I'm going to probably hit a corner. So maybe this is not viable. But what about this one, right? So I see these two. I see this one, and I see this one clearly. I can't see this one, and I can't see this one, right? So they're where I am right now, I can't see them. So instead of going from here to here to here to here, I'm going to go to the pivot location that has no obstacles from here to here. I'm just going to go right here first. That's my first step. So that kind of might be an optimization. Okay, how about here? When I've gone to here, can I see this one or this one? No. So then the next pivot path would be here. That would be the next possible path, right? And then from here to here and here to here. So I could smooth a little bit, all right, if I did it that way. What this does, the other way of doing it is, as we move across, and the other way of doing it is we do it in real time. So we start moving this way, we move a little bit, a kind of a time step. Okay, cool. Do I see a path that's better to get me over here? Yes. Let's start angling my ship outside of the grid. I'm not snapping myself to grid in this case. And then let's keep on optimizing as I go, right, to get to the next particular node, So this is what we want to do, this gray path. And there's different techniques to get us there, okay? So that's what path smoothing is all about. And we have to talk about it. By the way, I don't expect you to do path smoothing at all in any way whatsoever for assignment 2. Okay, it could be as granular as you want at the end of the day. So there's no requirement for path smoothing as long as you don't have any collisions. So if you have an obstacle, my expectation is that you'll avoid obstacles with your grid, right? But if you have something that looks like this, yeah, no, I don't expect you to do some optimizations. So points of visibility, again, going back to that, is we talked about, kind of these pivot points or inflection points, which is kind of a neat thing, right? So the inflection points, the points where you're going to start turning, can provide a hint as to how to get better smoothing happening, okay? So again, we can have our original path. This is our original points. And then what we want is some kind of offset, which offsets away from the walls, as an example. And you can see that you're going to get something between the offset and the points of inflection that we're seeing here, right? And again, using points of visibility, which is kind of interesting. So again, another way of doing path smoothing, all right? Which is what we're doing is we're bending along this method over here with some kind of offset from the points of visibility. So what path smoothing does in this case is it takes a look at all of these corners, right, and says, okay, so these are all the corners. I have a goal to get me somewhere over here from somewhere down here, as an example. How can I create a path that's between, the areas that I can possibly collide, right? So there's an area here that I can possibly collide, these two areas. Can I create a pathway, an offset between these two areas that I'm going to travel, right? So I don't collide with the corners, right? And it looks like it's a smooth kind of curve as opposed to kind of a rough turn. Okay. Points of visibility can also assist us. That's why points of visibility are great. It can also assist us with different patterns. So again, think about connection between nodes. You have a lot of different connections. And because remember, we talked about in our grid system, the great thing about a grid system is it has a limited amount of nodes. And this is a non-directed graph so that the AI could really travel from here to here to here to here to anywhere that it can really see, okay? It can't see this node because of this obstacle. So there is no direct connection from here to here, and there's no connection from here to here directly. We have to go through a visibility path, right? For every point of visibility. So I go here, what can I see from here? Well, I can see this one, this one, this one, and this one, but I can't see this one, right? So that's the way points of visibility works, which is kind of neat. And so what it does, but we have to keep track of all the nodes, and for every node, you have to know all the paths from that node, right? So that can, again, increase the amount of memory requirement depending on how many nodes you have. The more of these points of inflection or points of visibility, the more memory required as we increase the amount of nodes. And here's an example of that, where you can have more nodes. But the one way to do it, another division scheme, is using something called a navigation mesh. Okay, so here's a navigation mesh. And I'm going to talk about a navigation mesh really quickly. And one thing that we use with a nav mesh, Unity uses a nav mesh when it comes to their system. And I'm going to kind of, in a little demo in a second, I'm going to pull up a Unity project. We're going to make a new Unity project. I'm going to show you what a nav mesh looks like really quickly when it comes to, creating these points of visibility. So what a nav mesh does, it says, okay, well, I want to take my grid. So here's my grid. and I can divide it into a real-time mesh. So I pre-bake my mesh where I break the mesh down into different areas, right? By subdividing it into these triangles or triangular areas, right? So here's an example where I have a rectangular area and I've broken it down into several triangles. Each triangle, you go from the center of each triangle to the other center of the triangle, and that creates pathways from one area to the other. Now, the way this would occur, there's two ways of doing it. Again, you can have a floor polygon, right, as an example that you could create first. So first you create these areas, right? And what you want to do is notice that there are these edges, right? So here's edges. So at the very base, when I start creating a nav mesh, I kind of connect all the edges with all the other edges. Look at these edges here, right? So again, what I mean by that is, let's annotate this a little bit, right? So, which is kind of neat, right? Let's make that red color again happen. So I start drawing these nodes here. So I start drawing a line from here to here. So this is a subdivision. This is a subdivision, right? This is a subdivision, right? And so is this one. I can't cross lines. So depending on where I do the node and depending on my winding preference, I have to have at least one line that connects these nodes together. That's how this became this way, because there's a node here, like an edge here, an edge here, an edge here, because this is the way the graph is defined. And this is pre-baked, my friends. Okay, it's not something that happens necessarily in real time. Okay, now, so these ones, again, if you're entering from this way, is one thing. And then it looks to me that this is kind of a simple generation. You could have also made another subdivision down here by connecting these two things. You could have, right? So I could have done something that looks like this instead of the way the black lines look, right? Because these are simple nodes of connection, right? So I'm subdividing these things, and I can still subdivide it this way, right? Where I'm connecting these areas here to these ones. So these are valid, right? But I could do the same thing over here. So I could subdivide my mesh kind of in different ways. And, you can create nav mesh in different ways. So this is another way of doing it. I'm just taking the same map and I'm subdividing it in kind of a different manner, right? To create our navigation area, right? And by the way, these also require a little bit of a mesh. Notice that the mesh also extends in here where you take the original mesh for the doorway and you have a couple of nodes for each of the meshes. So what you're starting to do is you're creating subdivisions. And then when you have a subdivision like this, and now look at all these points. These are all points here on the hexagon. And that's where these additional nodes came from, where I take this node and it connects from each point of, or whatever this polygon is, right? This multi-point polygon here. And that's where these additional divisions come into play. Because you want to avoid kind of connecting or colliding with this area here, okay? So again, that's how the navigation mesh is formed. And once it's formed and you have nodes, as an example, I'm just going to undo those changes. So once you have nodes, node placement basically happens in the center of each subdivision. So example, that would be the center, this would be the center. And then once you have all the centers, now you have pathways. Right? Notice that there's only one node for each subdivision, right? That's how it works. That's your nav mesh, right? And so now you have a way, and notice also there's only one connection. It's not like each of the nodes have multiple connections, right? They have like one connection or whatever or two, let's say, from one node to the other. And some of these have more. But you can see that you can reduce the complexity of your path by basically the way you're connecting the nodes. Okay, so kind of interesting way of doing things. So navigation mesh. Okay. And yeah. So one thing when it comes to navigation meshes, or nav meshes as they're called, if I have a character that's off the ground, let's say for example I'm on a platform or something like that, then what we want to do is be able to travel, so an off mesh connection point, if you will, from one part of a navigation mesh on a platform down to an area where there is, again, another navigation mesh. So we have to be able to kind of connect from one polygon to another based on the new navigation mesh. So notice there's a navigation mesh here, here, and here. And I'm going to travel from here, here, and then from here across, and then up to this one. Or I can jump from this one over here to this one if I have the momentum, or my autonomous character can make that jump. Okay, so that's one way of doing it as well. So there's also going to be some points where it may not be valid, and sometimes what ends up happening is this situation, right? Where, again, corners are always a problem when it comes to navigation, whether it's an outer corner like this or an inner corner like an elbow in here, right? So an inner elbow or an outer elbow, a corner, right? Doesn't matter how you look at it. It can be problematic because of collisions, right? Depending on, because these are the exact, let's say, centers of these nodes, right? If these were the centers of the nodes, then going from one thing to the other might end up in a collision area right here. So that would be a problem. We also can use the edges as nodes, right? Where each node itself uses an edge to kind of define a node as well when you create your navigation mesh, right? And you can also use, notice that there's different node connections. This is another way of doing it, right? Where your subdivision scheme is based on line of sight. So, example would be here, right? I would go here, 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 and here. Those are the points. There wouldn't be a point in between, right? This is my navigation mesh, right? And the point of intersection between where my start is and my goal is, that area of intersection there would be the next possible node for traveling. Thanks to Frank. So that is the way it would work. So this is kind of, these are the nodes that it would pass through, and these are the exact locations where it would move to. So if I'm navigating, even if I'm using something like steering behaviors, I'm going to move to these 3 nodes. Whereas if the start and end goal were different in the same exact navigation mesh, you could also use a navigation mesh so that it moves from here to here to here to here. Again, you can see that the nodes would change. So I would go from here to here, an actual target, right? From here to here and from here to here. It looks like a straight line, but actually there's a few nodes here. And this idea can be expanded upon when it comes to, kind of navigating around a world. Here is an example of a world where the character moves by a direction and 90-degree rotation. So where the character can't move, as an example, in any direction they want. They can't do 360-degree movement. They can't move in diagonals. This is kind of where we've asked you to do. All right, we've asked you to kind of make it so that you can only move in the direction that you're looking. Right. So example would be, I can only move from C1 to A1. Right. I can't slip over this way. This is not a valid location, as an example. Right. And so I could turn, right? I can turn to the right, right? I could turn down, and I can turn to the left. Notice these are the moves: up, right, down, and left. So those are all possible positions for each of the nodes from A1, B1, and C1, right? So similarly, if I'm moving from C1 to A1, I move forward, and then from A1 to B1, I need to turn. Right, so I turn, I rotate 90 degrees, and then when I turn, that's a move. Actually, that takes energy, and then I move to B2, and then from B2 I can move to the next location. So it goes from C, I turn, rotate 90 degrees to point upwards. From C4, I move into C. It becomes in this position. See, this is my C4 state, and this is almost like different states of my autonomous character, where a state is not only a location, but also a direction that they're pointing in. So in this state, if I'm looking this way, that is my C4 state for my autonomous character. Where if I move from C4 and I want to move into C1, the C1 state, I'm going to point up, right? That's where I'm moving towards. So it's not only location, but also direction. Okay, so different ways of thinking about moving around the world. When it comes to path smoothing, we kind of talked about this briefly earlier, which is how do I figure out a way of using a steering algorithm as an example to move through a path, right? So again, not just the moving around the original path, right? So the original path is this black path, right? And if this, assuming again that I have diagonal movement in my path, again for us, it won't look like that for your particular game, right? Because your assignment 2 is not going to work like that. It's going to more work like this, kind of from here to here and from here to here, and maybe from here to here. I'm just choosing another path, and this might be the path that it takes. So this might be your original path. But again, how do I optimize or smooth this path? It's kind of like saying, well, points of inflection again. Can I see from here to here, right? As an example, let's just change the color. Can I see from here to here these points of inflection? So can I go from here? Can I see this path? Well, maybe because of this little corner, and I'm passing through a corner where I'm gonna collide. Maybe there's a width requirement. This is not viable for me to go from here to here, like I said before, right? Can't go from there to there. Can I go from here to here? Certainly. Can I go from here to here? Most likely, right? So this is definitely a path that I can go to. And that might be a smoother way of moving than going da-da and then going this way. This is actually faster, right? And then again, now I'm here. Can I see the end goal? Yes, but I'm really close to this corner here. And if I have a width requirement, I have to pass through another area. Maybe instead of going this way, this might be a better path for me from a smoothing perspective. Right? I'm re-smoothing based on our requirements, right? Because this is my path, not the other one that I had before, right? So again, I could go here and from here to here, right? So that one might be the smoothest path possible based on, these straight lines. And I mean, again, is this optimal? It's definitely only 3 steps, 1, 2, 3 before we get to our goal, as opposed to what we had earlier, right? Which is 1, 2, 3, 4, 5, right? There's 5 steps before we get to our goal. So 3 steps compared to 5 steps, that's a smoother algorithm as an example. And we can use, again, points of visibility. Can I cast a line, a ray from my character, right, in the direction of or towards my my goal? Can I see my goal? If I can just do from this, that would be the best path, right? From here to there. But I can't because of this, right? Because of this corner right here, right? So I need to find the next best path. And instead of doing it in real time, I'm going to do it in chunks, okay? So that's kind of what's path smoothing is around. And I'm hoping that you get that there's a better way of doing it. Again, do I require this for assignment 2? No, I don't, okay? And there is some algorithm I've shared with you here, right, in terms of path smoothing and so on, and how to, how to do that as pseudocode. Okay, any questions around this before we get into the demo that I want to do with you for with Unity and navigation meshes? So again, we've discussed basic pathfinding, and there's different division schemes. So this lecture is all about division schemes. How do I divide my game world into something that makes sense? Do I use the tile and grid system? Do I use points of visibility? Do I assign a cost to turning? Do I increase the movement cost when it comes to moving across difficult terrain? How do I do this kind of stuff? And what makes the most sense when it comes to my autonomous agent moving around? But let's talk about that thing in more detail, more of a graphical detail about how to create this idea of a nav mesh, all right? And how it's done by a kind of a commercial game engine like Unity. All right, so let's do that next. So in this demo, I'm going to be using Unity version 2021. All right, so let's just pull this up. I'm going to pull up Unity Hub here, and I'm going to make a brand new project. Again, I don't expect you guys to follow along in any way. So it's just a you watch and I do kind of thing. And we'll explore some of these things as we go forward. Okay, so I'm going to make a new project based on 2021. For Unity, again, there's different ways of, as a commercial game engine, I have options to create different templates. Again, I'm going to use the 3D template, which is a basic template, and we're just going to call this, a nav mesh demo. All right, that's really what this is about. And I'm just going to put this, I'll share this with you later on. So if you want to check this out, I'll put this inside of our GBC area for GAME3001 in the summer 2021 semester. And we'll just use this as a nav mesh demo. That's what we'll call it. So in here, that's what it'll be. So I will share this with you later on up on Blackboard. Okay, so let's do that. So create. And what Unity will go and do is it will create a, kind of a general area that we can play within. I want you to think about what we're doing here. Even though I'm using Unity, and normally what we do is we use C++ for the stuff that we're doing. Remember that a lot of the stuff that's been developed for Unity came out of, I have an editor area, and my editor area needs some kind of controls. I need some kind of, panels and those kind of things that can come up, right? Well, those panels, think about them as kind of like an expanded version of IMGUI, which is kind of what you're doing, right? So that's something that what we want to do. You can see that even with my crazy system, this is taking a bit to start 2021. Okay, I'm just going to wait for this to be done in a second. So system specs for me, again, I'm running an i9 RTX 3070 with 64 gigs of RAM right now. So it's pretty crazy, but you can see that still sometimes to generate a Unity project can take a bit of time, right? So let's see how this works. Sometimes it'll be like lickety split. It'll generate it in 2 seconds, right? But for me, it takes a little bit of time to do, especially since I'm broadcasting and I'm broadcasting. So there's my Unity workspace. Now I use maybe a different Unity workspace than you've used to. I have a scene view. Again, this is where all the action happens. I have a game view, which is something that you're going to see in real time, right? As an example, I'm going to get stuff from the console, and I also have some animation stuff happening. On the right, it tells us in our hierarchy, again, if you're not used to Unity, right? It's enough, definitely. If you have a 3070, it's enough for what I'm doing. And in the hierarchy, you have these points. I'm just going to turn gizmos on so you can see them. So I have a directional light here in 3D, and I have a main camera, and the main camera is looking at things in a perspective view, okay? So what I want to do is for this demo, in my sample scene, first of all, what I like to do with scenes is let's rename our scene something that I like to use. I kind of use an underscore for scenes. As an example, sometimes people also use curly braces or square brackets. I've seen that lately as well. And I want to make a new folder for scripts if I need that. So those two things, scenes and scripts, are basically the two folders I want to use. In my scenes folder, I want to rename this to main, because this is our main scene for our sample, which is going to reload my scene. And now what I want to do is I want to add a couple of simple things. One of them is going to be some kind of plane area. So let's do that. So we'll add a new 3D object plane. All right, so it's kind of an easy way of doing stuff. So there's a plane. And this is where what we're gonna use for our object to navigate. Okay, so we're gonna have a target, and we're gonna also have a some kind of autonomous agent. All right, so that's what we're gonna have. So this plane, let's call this plane ground. And let's add some color to the plane. And I'm gonna use a material for this. I'm gonna make a new folder called materials. And in my materials folder, I'm going to make a brand new material. A material is kind of like a program that allows me to attach a texture or a color to a surface of an object. So let's make a new material for this, and we'll make this the ground material. And the ground material can have a some kind of color. So I'm going to change the albedo property to include a color that's more like a green color or a brown color. Let's just do a brown color. There we go. So that's the ground color. And then what I can do is I can attach the ground color. Ooh, that doesn't look quite brown, does it? I can attach the brown color that I want, to my surface. There we go. It's more of a brown color. So that's my brown color, and I'm going to use that because then you can differentiate between the ground and the surface, right, and other objects in the ground. So my game actually looks like this because my camera is looking at it as an example from this perspective, right? Let's add two objects. Let's add a target. So I'm going to make a 3D object, which is a cube, right? That's my target, okay? And my target is kind of half sunk into the ground. I'm just going to pull this up across the y-axis 0.5 units, so it's sitting on the ground. We're going to make the ground bigger too in a second. And let's make the target have a material as well. So we'll have a material for the target. We'll call this the target material. And the target material will be green, right? So that is my green target. And I can just drag and drop that material on top of the target to assign a value, right? So pretty straightforward now as what we have. So a target, and it's just a cube. And we'll have an agent, right? So let's make an agent as an example. So a 3D object. And we'll make the agent a cylinder, right, as an example. And here's the cylinder. It starts in the same location because they're kind of overlapping right now. But what I want to do just for the agent, like I've done before, is move the agent up above the target area. And notice that the agent is actually half buried. Let's move this even further up until the agent is kind of sitting on top of on the ground there, right? Again, you can see these arrows are the ways I can move across different axes. So this is across the z-axis, this is across the x-axis, and the green is always the y-axis. And in Unity, y is up. That is the standard that we use here, okay? Let's make a new agent material. So again, I'm going to make a material for the agent. We're going to call this agent, and the material is going to be red. All right, so there's my red material for the agent. I'm going to drag and drop this on top of the agent, and you can see that now the agents are red. The target is green, and the ground is brown. Pretty simple. Let's make the ground bigger, and I can scale it up. So there is a position, rotation, and scale. Look at that. We're using a transform here as well, just like we did in our game world, right? So I'm kind of doing the same thing here in Unity that I did in our game world. Let's expand this by 2 to make this kind of twice as big as what we've seen before, right? So there it is. So it's twice as big. And we have our target. We can move our target around, similar to what we've done with our agent. We can move it around here. So there's our target. And I can kind of fly through so you can see what it looks like, right? I can use fly control. So when you right click in Unity and use your WASD keys, you can fly around just like you would in any other kind of like first person shooter or video game. All right, so there we go. So this is where I want to go. This is where I am, and I want to create a nav mesh in order for me to do that. So when Unity creates a nav mesh, what I can do is I can start right here on the right. Okay, here's the right where I have lighting. I can have another window in here that shows me my navigation. So again, under Window, right, you can see that there is AI, and underneath AI, there's a navigation window, right? So navigation window is kind of here. And what I can do is I can look at both agents, and it talks about an agent by default is humanoid. My agent has a radius around it of 0.5 units, right? A height of 2 meters, that's what it is, approximately. I can make that height smaller. The height of the agent makes it so that it can decide whether it's going to fit through an opening like a door. That's what it does. And there's also a step height and how high the agent can step up. 0.75 units, and the maximum slope that it can go up in terms of stair slope. Okay, that's what it does. So there's the slope, and there's the stair height. That's what it looks like, so it can go upstairs as well. Okay, so that's your humanoid agent. You can add other agents in Unity as well, as much as you like. Okay, and what I want to do now is when I select a ground area, right, as an example, then when I go to areas, there's different things I can make in Unity. I can assign things like a walkable area, a non-walkable area, as well as an area that I need to jump. Notice that the unit in terms of value, I can change the value of these units. I can make, for example, a swamp area or some kind of forest area. And when I can increase the value of walking in the swamp or the forest. Let's say, for example, walking in a swamp is 3 costs. Walking in the forest is only 2 costs. same as jumping. And what about walking in the sand? Maybe that's going to be something like 4 costs because it's slow. So these costs will be something that the AI takes into account in terms of walking. We're not going to care about this today. All we're going to care about is a walkable or non-walkable area. When I go to my bake area, right, so if I select an area that I want to bake, I can literally just click on bake, and what it'll do is it's going to bake the area that I've selected. That's typically how it works, okay? So notice that it can, my mesh renderer, right? So this is the navigation mesh, right, that I can create. And what I want to do with the ground, the reason why it's not showing a bakeable area is because I really don't have anything on the ground except for my mesh renderer. Let's take a look and see if we can add a component to help us out. So if I click on this and if I start typing navigation, right, we can look at a couple things. One is a nav mesh agent, and the other one is a nav mesh obstacle. So I want to have both the nav mesh agent and the nav mesh obstacle, okay? So that's what I want to kind of do. First things first. So let's make this a nav mesh agent. All right, so I'm add a component from my object, and we'll make this the nav mesh agent component. The nav mesh agent component basically says, hey, look, I've got a humanoid. That's the agent type I'm using. Here's my speed and everything else we defined before as an example. And it has things like angular speed, how fast I can turn, my acceleration, stopping distance, and so on. And one thing that we're going to do in code is we're going to have our target, as an example, as the destination of my nav mesh agent. That's what we want to do. And we want the nav mesh agent to move across the nav mesh, which is what we want to do here. We want to establish a mesh that's here, a nav mesh that's in our plane, okay? So that's what I want to do. So I want to be able to go to the nav mesh, right, as an example. One thing also it says that, it says for objects, we can do things like create a navigation static that is a walkable area, okay? But here, I want to be able to bake this area right here. So how do I bake my agent? How do I bake my stuff based on my workflow, right? So this is what I want to do here. I want to bake my navigation mesh. And we want to bake it. We don't want to bake it in real time. We want to bake it beforehand, right? So we want to kind of select a floor where we can have our object baked. That's what we want to kind of do. So when I select this, I want to bake my object and it's going to be done. Okay, and that's what I want to do. And what we want to see after it's been baked, and by the way, if I use a plane, right, a plane, think about what a plane is in effect, right? So gizmos, this is one thing. Gizmos allow me to, in Unity, allow me to select and deselect objects. So sometimes when you have these objects not being seen here, as an example, then, what it does for each of these objects, right? For each of these objects like the ground, we can kind of show different parts of it. For example, I can show a wireframe, right, of the objects if I really want to. I can show a shaded wireframe where I can see not just the object, but also the way the object is put together in the renderer, right? So here we can see that this is the shaded wireframe of each of the objects, right? Where we can see that the object itself is broken down into several smaller triangles in order for us to print it out. Okay, that's how it works. Right now, if I was to run this thing, by the way, it doesn't really do much, right? Because whether I bake the navigation mesh or not, we just see this little thing right here. What I want to do is I want to move the camera so we can look above this thing so we can see the plane. So the camera right now, if I click on the camera object, you can see that the cone, the camera's frustum, which is kind of like a cone-like structure that points away from the camera, is kind of looking at this area right here. And this is a preview of what the camera will look like. What we want to do is we want to move this camera up, and we want to rotate this camera, let's say something like a 90-degree angle so it points to the ground, right? So again, you can think about rotation across the x-axis that we want to do. So if I rotate the camera across the x-axis approximately 90 degrees, it's going to point toward the ground. And then what I can do is I can kind of move the camera up, right? So we can see the entire frame. And across, this is the preview again, right? So and across hard to see, sometimes see in 3D, well, we can see this is kind of what we want to see. Again, I'm turning around so you can see this whole area here, right? And we can see the entire kind of game world. Okay, so that's what we want to see. And we want to see it so that this shape, that's the goal. The goal is for this shape to kind of go across and go to here. Okay? So that's the way it works. So now when I look at the game, you can see that that's exactly what I'm seeing. I'm seeing an object here, and then there's an object here, and I want to go from here to here. And we're going to use a navigation mesh to do that, right? And here, okay? So again, if I run this thing, right, when we run it, you really don't see any movement because, you know, we just have this thing and nothing, there's no scripts or anything like that for us to move. We know that the agent, as an example, not the material, but the agent itself, which is the cylinder, let's call the cylinder agent. I probably should have done that in the first place. So here's the agent. We know that the agent, right, as an example, needs a target. And what we can do is we can add a little script for ourselves to kind of view the target. I'm going to make this new script. I'm going to call this agent behavior. So I'm going to kind of make a new C# script here, which is similar to attaching a C++ kind of onto an object, right, kind of. More like it's scripting. So what I'm going to do here is I'm going to call this agent behavior, keeping it simple. And here's Visual Studio. What I want to do with Visual Studio here with my agent behavior is notice, hey, I have a start script and I have an update kind of function, right? So isn't this similar? So this is how we've kind of put together our SDL you know, kind of engine. We put it together so it kind of feels like the same kind of methods that we use in Unity. That's what we've done here to make it easier for you to eventually move to Unity when you go to a you know, kind of a commercial game engine. So in the start script, you want to do a couple things. I want to get the target object. So I want to get a reference to the target object, which is my target. So let's just do a game object. And we'll make this public, make it nice and easy. Public game object, which is the target. Okay, that's the target. And then what we can do, I can attach this you know, agent behavior to my agent. So again, going back to once it rebuilds the scripts, I can go to my agent, and then I can add a component, which is my agent behavior, right? And when I do that, you can see that I have a target area that's open to me because I made it public inside of C#. That's how Unity kind of works. And I can just drag and drop my target as a reference to this, to the agent. So the agent now knows about the target. So there's the target, here's the agent knows about the target. Then what I can do is I want to also get a reference to the agent's navigation mesh, the nav mesh agent. I want to get a reference to this, right? And for this, we need to add using Unity AI. So using Unity Engine AI, that is a script reference, right? So I'm kind of making an assembly reference for this, right? And then what I can do with this is I want to make a reference to the nav mesh agent. So if I start typing nav mesh agent, right, we'll just call this agent. That's kind of thinking about this agent itself. I can make a reference to it by just saying agent is equal to get components nav mesh agent, right? Again, don't worry about how this works. I'm just making a link between the actual component that I have in my game and the agent itself. And if I was to run this thing just for a second, right now, publicly, what you're going to see is that there's no reference to the agent. But when I run the game, during runtime, you're going to see that it connects to the agent, the nav mesh agent that's found right here. Okay. So what I can do with the agent is I can say that in runtime, I can say agent dot, and again, I can set destination, right? And I can set the destination to a vector 3, not like a vector 2. A vector 3 would be the target, right? So here's my target. And I need to find the target position. Remember, position is part of all game objects. It's part of a transform. All game objects have a transform in Unity as well, right? So it would be the same thing. I'm going to say target dot, and I want to look at the transform dot position. So this is the location of the target in the game world. So my agent destination, set destination, is going to be the the position of the target. Now, the problem with this is that there's no nav mesh yet, right? So this is the first part. So if I was to run this thing and I ran the object, it's going to give me a bit of an error. It's going to say, I really don't know. There's no nav mesh, and la 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 la. See, it says set destination can only be called on an active agent that has been placed on a nav mesh, right? That's the error that I'm getting. But it's actually working right now. It's kind of already working. I already know where the target is, and I already have something that's working in real time. Nahar says, will we be going over C# and Unity in the future? Not in this class in particular, but maybe in our class for physics. What we'll be doing is we'll be thinking about how to, how to do stuff. Definitely not now, but in the future. For example, one of my courses that I'm running in September, right, is a mobile game course, and we do full-blown Unity in that course, right? So you're going to learn about Unity and game engines in third year for sure. And a lot of times what we do is we kind of want you to learn all the C++ stuff and the Unreal stuff as early as possible, and then get you into Unity later on. Because Unity is kind of a simpler, easier way of doing things, and it's better for you to know the underlying APIs that are going on here than just showing you, teaching you how to use Unity from the very beginning. Because anyone really, Unity, you can see how fast I've done this, right? I've got a lot of stuff that's already partitioned in here. All right, so then why isn't it then that when I click on the object, right, here's my object, I clicked on the ground as an example, and I haven't been able to create a nav mesh agent. What's the problem with this, right? Well, notice that it has a mesh renderer and all this kind of stuff here, right? That's one thing. And the other thing is, like, what if I selected something else as a navigation mesh? So let's say make a new object. Let's make a new cube here as an example. Here's my new cube. And let's suppose that I made this cube like, 10 times larger and 10 times taller, the big cube, massive cube. And what if I did this again? I went to navigation. This is kind of how we do it, right? I went to navigation. And, I go bake, right? Well, it's not going to work there either, right? So it's not the type of mesh, right? That's the first thing that you're like, by the way, notice that the parallax we got there, we thought that the cube was underneath the other one, but the way that this is looking, it's kind of deceptive where it is in 3D space, right? So one thing to know. So it's not the type of object that we want to put together. So let's see what Unity tells us in terms of how to put together a nav mesh. And this is something that I want you guys to learn about when it comes to, if you're going to use or play around with Unity at all. So if I go nav mesh in Unity, how do I do that? And it really talks about how to do that in Unity. So the first thing is it says, select the scene geometry that should be affect the navigation, walkable surfaces. Check navigation static on to include selected objects in the nav mesh baking process, right? So click. See that? Object, navigation static, and then bake the mesh. So let's do that. So again, click on this, go to object, click on navigation static, and then go where it goes to bake, and I click on bake, and then you can see the navigation mesh come on really quickly. Take a look at that. That's what it's done. It's actually subdivided. I'm just going to take away this shaded area. It's actually subdivided this mesh into this area here. Now I have a navigation mesh, right? And if I click play, and if everything goes well, then we should see our object move towards my my other object, and it's going to kind of go inside of it because there isn't any kind of colliders that are going to stop it. Okay, so that's an example of how the navigation mesh works like. It looks like if I was going to make a navigation mesh like this, then that's great. What I want to do now is make an obstacle, so to give it this thing a challenge, so that it has to go around the navigation. Kind of use the navigation mesh to navigate around the obstacle, right? And we want to put it in the scene. Let's turn off gizmos for now so we don't see the mesh while we do that. So again, I'm going to make a brand new object. Let's make a 3D object. We'll use a cube again, and we'll bring it up into the scene. There's the scene. And what we'll do is we'll expand the cube. Now, there's different ways in Unity to do that. Again, and we can go into my inspector here to see the position of the cube. We want this to be definitely 0.51. Well, what we can do is with Unity, you can also use a different control to expand the cube, right, in different directions, right? So depending on how you're looking at the cube, you have the ability for you to expand up, and you have the ability to expand wide. So you can modify the cube in real time to make it like a wall, right? That's kind of cool, right? Let's make a new material so that we can separate or divide our surface so it looks like, actually we can use the same ground material for this. So it looks like part of the ground. Okay, so we'll go, okay, there's part of the ground. And we can see that that is kind of an object in place. And let's move it around. So we're going to move it in between these two objects. So we're going to make it so that this object is here. And I'm going to rotate it around the y-axis, right? So that way we can kind of make it so that it is in place in this weird space here, right? So there we go. Let's make sure that this is 0.5 position across the y-axis. Okay, there it is. So then now our nav mesh agent, right? Let's put them over here. Let's see what happens with them when they try and move around this obstacle. Let's see how that looks actually. Yeah, you really can't see it. Let's make a new thing for obstacles. Let's make the obstacles like black or something. So again, I'll make a new material, and the new material will be kind of a dark material, like more closer to black or a dark gray, let's say. And yay, and we'll make the new material, we'll call this the obstacle material. And we'll just take the obstacle. This will be the obstacle right here, right? And we'll take the obstacle and drag and drop it across on top of this one so you can see it now in real time, right? And then if I press play, what we want to do is we want to make sure that this thing goes around the obstacle. In order for me to make this obstacle part of the nav mesh and rebake it, we need to go to navigation. Well, first of all, let's add a property to the obstacle. So in the inspector, we're going to go add, and we're going to go nav, and we're going to make it a nav mesh obstacle. So a nav mesh obstacle basically creates a box around this area here that allows us to define that this is an issue, right? An obstacle that we can go around. And then in the navigation, right, we want to rebake our area. So let's turn on gizmos again. Notice that this is our gizmos. And if I click bake again, what I want, if the obstacle was something that's cool, if this was normal, then we would bake an area around the obstacle. So far, it hasn't happened. Why? Well, the object itself has to be a nav mesh static, right? Again, we have to click this on. I want to select this. I want to go bake, and I want to click bake. And you can see now what's happened is that the navigation mesh has baked around or carved out an area around the obstacle. And take a look exactly how we saw that on the PowerPoint document, where we have our navigation mesh subdivided an area based on the corners of the obstacle, right? And some kind of offset. So from the obstacle corner, it has a little bit of an offset, and the offset itself, it creates 2 additional points of navigation so that we can navigate the obstacle or the object around the obstacle based on the radius of the agent. Okay, so again, if I look at this now and if I press play, what we should happen is it should navigate around the obstacle without quite touching it. Okay? And that's how easy it is to set up a nav mesh. This is what a nav mesh does for us. It allows us to build a level, right, where we can create obstacles in, kind of in design time, right, that will allow the agent to move around. Let's do a couple of other things. In Unity, we have a prefab system, right? So if I make a folder called prefabs, where I can prefabricate or create instances of the same object over and over again. So in my prefabs folder, I want to drag a couple things. I want to make an obstacle a prefab, and I also want to make my agent a prefab as well, right? So there's my agent. So I can make multiple agents. So let's drag another agent to the scene. There we go, right? And the agent should definitely be in the same height as everything else, so kind of 1. We'll make 2 agents, right? And we'll kind of duplicate the obstacle, put another obstacle in the scene here too. Make sure that the obstacle is, again, 0.5 out from the thing. And we'll make it so that it's rotated slightly differently than before, right? So again, we'll do a rotation that's kind of, I don't know, maybe something like this. And we'll move this across this area here. So let's see what happens if I pre-bake the mesh that looks like this now with 2 agents, right? So again, clicking on the mesh, I'm going to go to navigation, and then what I want to do is I want to rebake everything again. Just click bake. You can see now that I have two areas that I'm baking around with the navigation, where I'm hoping that the agents are going to move around the mesh. Now look, there is an area that is blue here, and blue means good for Unity. It's going to be able to move through here and go to my my object. Let's add one more obstacle to make it more interesting. So again, I'm just going to go and drag and drop another obstacle over here. Make sure again that the obstacle is at 0.5, so it's not buried in the ground, although burying in the ground would be okay. And let's rotate this again just to give it a little bit more interest, right? So we can see what this looks like if I was to move it across a much narrower area here. Let's see what happens when we rebake the mesh now. If I do this and go to navigation, let's see how it rebakes this mesh now. Does it give me an area to pass through over here? Well, obviously it doesn't, because when I rebake the mesh, it kind of combines this mesh around this one. So this is what navigation meshes are. They kind of look at obstacles or borders or whatever in the scene, and it kind of calculates whether an agent can pass through an area like this or around obstacles in order for us to get there. Let's add one more obstacle that kind of cuts off this area over here completely, right? So again, I'm just going to duplicate this one in scene. So Control D to duplicate this, and I can pull this over and then just rotate this around here like this. Again, it's pretty messy, but who cares? It's just really made for demo purposes, right? So I'm going to make it so that there's definitely no way to pass through there. So we have a series of blocks. It's the only way, viable way is up here or through here. Let's see which this agent goes through. Will it go through this way or take this path? Let's try it out and see what happens. Oh wait, I didn't really bake the mesh. It's going to go right through this obstacle. Let's see what happens when that happens. We got a bit of an error, right? One thing at a time. All right, so let's see what happens. Oh, one thing is the target. We didn't specify the target for the agent because of the way I did my scripts. That's okay. Let's put the target in here as well. There we go. And I needed that. That's what the error was. And let's rebake the mesh because I forgot to bake the mesh for this particular obstacle. Let's do that now. Excellent. And you can see clearly that that is carved out. So there's no way, because this area is not blue. Only the blue areas is where these agents can travel, right? So you can clearly see that there's no area that the agent can travel over here. All right. Let's try this again and see what happens as we move through. So you can see that it's going to move through. Both of them are going to try and move through this area here, and they're going to slow down as they navigate around the obstacles, right? And they're going to try and fight for control because these guys are going to try and get as close to the target as possible, right? We can change that by going to the agent itself, right? The prefab for the agent. I can modify the way the agent moves in terms of our distance. So you have a lot of little things here. For example, angular speed, accelerations, and stopping distance right now is 0 units. Let's give it a stopping distance of 1 so it won't go, too close to the target, okay? And let's also pull this agent a little bit towards this side and see if it's going to choose this way over this way. Let's see what happens, and it will, right? If you were to do this, right, you're going to see that one goes in one direction where the other one goes in the other direction, and then it kind of sits at the target. That's not quite right. Let's try that again, and let's make sure that these agents, Agent 1 and Agent 2, let's give them a more of a stopping distance than 1. Let's make them so the stopping distance is, I don't know, 3. All right? And one more time. And let's see what happens. All right, so that's kind of close enough to the agent. All right, questions around nav meshes. So really a nav mesh, what it is it's a piece of geometry that's being drawn on top of another object. You can clearly see that this is a mesh, a geometry that has vertices, and it's been created by basically taking these vertices or inflection points from the corners of my obstacles, right? Even the corners of this thing, and creating an offset based on the walkable area, which is really the radius of my agent. If I change the radius of my agent to something smaller, then what it can do is it will be able to navigate into a smaller area in here. Here's an example. Let's say I move this to a radius of 0.3. right? That means my agent is actually a lot thinner. That's not really true, which means these can probably collide or go through objects now. But I have to rebake the mesh based on these new parameters. So if I click this object here and rebake it, take a look at the distances between objects now when I do that, right? It becomes tighter, which means that, hey, I can move anywhere in here now, not just, and it's going to move in the middle, right? It's going to kind of have this target where it moves in the middle of these areas anyway, but it's still not quite thin enough to pass through this area right here or this area right here. However, if I was to move this block, right, that might be thin enough for this thing to move through if I do it again. Let's rebake. Right, yeah, see that? That's pretty thin. So now my agent thinks it can move through this area right here and through this area here. Also notice, because I've changed the width of this object, it can even look at the tops of these obstacles, these areas here, as objects that it can bake. All right, so kind of cool. All right, let's see what happens now when I run it. What will it do now? Will it go through this way or this way? And yeah, it's going to try and move right through here without colliding. Look at that. It's going to squeeze through there and then go there and kind of find the right path, right? So that's how it's going to look. All right, questions around navigation mesh, a nav mesh. You should have a really, kind of decent understanding of what it is now as a division scheme for a game world. Again, in 3D, navigation meshes work fantastically. You can also use navigation meshes for 2D, but I think they're a little overkill in terms of the cost, in terms of memory and all that kind of stuff. What are your thoughts, guys? No thoughts. Yay! All right. I'm going to put this project up on eCentennial, on George Brown's Blackboard. Yay! And we'll do that. You'll have access to this project later on for yourself, so you can use it anytime you want. One thing to note is with Unity, whenever we want to put an object up, I'm not going to give you the whole Unity package. One question I always have is, how come I can't put my package that's really large up on GitHub? And the reason for this is because GitHub can't really handle large files beyond 100 megabytes without kind of activating the LFS system. Let's do that again. So I'm going to, one thing to note with Unity is we need to save project. And with Unity, it actually has good support for different version control systems. But the main one that it supports is Perforce out of the box, right? I know, I'm a traitor, Lyra. I'm so sorry. I do teach at different places. And sometimes I get confused, I'm sorry. But for the most part, what's happening is that when I want to do GitHub, I need to turn Unity off in order for me to do it properly. That's what I found. So if I turn Unity off, and if I go back to my command prompt here, just like we normally have done in the past, if I kind of teleport myself to the desktop, and if I go to GBC, and if I go to GAME3001 into the summer 2021 semester, you can see I've got my nav mesh demo. I want to go there, right? And if I do a directory, here is my files. Here's my files, right? And this is everything, including my library. One thing I need to note, I need to add for this one is a gitignore file. So let's do a gitignore file. And what I want, oh yeah, I'm not using PowerShell here. Sorry about that. Let's just drag and drop that into my Visual Studio Code for a second. While I do that, and I'm just going to grab desktop, GBC, GAME3001, and M2021, and we'll just grab nav mesh demo and pull it in there. And then what I want in here is I want to create a .gitignore file like we've done before. Now, automatically in Visual Studio, when we have a Visual Studio project for SDL, it generates a .gitignore file for us, but we want to make one here. So I'm going to make a new file. We'll call it .gitignore. And what we want is a gitignore file for Unity. What we definitely want is we don't want to respect .ds folders. So anything we put in our Unity our .gitignore file, it'll ignore. So that, anything to do with library, right? So anything /library, a /vs folder, anything like that, we don't want our stuff to put up, right? So anything .vs or library, right? Because if the library will be regenerated for us, right? In fact, I can just put library by itself, and anything .vs would be something that it's going to ignore. Okay, just these two alone are good enough. But if you want to find a better gitignore file, let's look at unity.gitignore, unity.gitignore. And there are some examples of where we have a Unity, gitignore file that you can use that I'm going to use. I literally just looked it up, Unity gitignore. I'm going to go raw here and just select all these and go back into my file and paste them. So I have a Unity gitignore file that I can use. And I've just saved it here inside this file, right? I'm going to go into my terminal window, and then VS Code is another editor that you can use that's compatible with Unity if you want to. I use it for a lot of times for JavaScript coding and anything to do with the web. It's kind of a quick, lighter editor than the Visual Studio IDE, which is pretty heavy duty, right? So here what I can do is I can do a git init, a git add dot, which only adds the stuff that we want in our working directory that does not include the stuff in the gitignore file, right? And I can do a git commit -m, which is initial commit, right? There it is. And now I need a repository that I'm going to share with you guys now. So we're going to go to github.com and we're going to go to George Brown. And under George Brown, I'm going to make a brand new repository here, and we're going to call it the nav mesh demo for GAME3001, and we'll call it M2021 nav mesh demo. So one kind of project like this, we'll make it public for you guys, and then that will be everything you need to access it. I'm just going to grab these last 3 lines of code here and do my work manually. And I'll push all this stuff up. Notice that it's going to push the entire project up without an issue. Why? It's ignored most of these things. Anything that's grayed out here in VS Code, it shows you which of the folders it's grayed out. When you download and install our package for that I'm sharing with you here, right? What it's going to do is it's going to, if you use Unity 2021, to run this package in the future, the great thing about this is it's going to regenerate the library, the logs, and the object files so that you can use it properly. Let's make a brand new README file for this. I'll say readme.md, and the README file will just use something like GAME3001 in the summer 2021 semester, and we'll say demo project for nav mesh. Using Unity 2021. Okay, so that's something I want you to remember. So this is the thing. I'm gonna put this up on GitHub. So say git add dot, git commit -m, and we'll say added README file, git push. So that's going to push everything up on GitHub. And when I go back up on GitHub and refresh, you're going to see that there's going to be a little README file that has this. So it tells you Unity 2021. That's what you need for this particular package. And I'm just going to take this whole thing and I'm going to put it up on Blackboard for us. So under Blackboard, you have access to this thing. I'm going to go to, again, to web link. And if you want to try this out yourself and fool around with it, you can there. This is the nav mesh demo with Unity 2021. Okay, so you can try this out if you want to. One thing also that I didn't do this week for, I guess I forgot, is the YouTube video. If you missed this, or if you wanted to look at this later on when it comes to studying for your midterm test, which is something that we're going to cover. We're going to cover all the stuff, the concepts that we've covered today. We're going to cover it for the midterm. It'll be here. You can kind of view in this video. So you can do that as well. Sorry about that, guys. Normally I remember to do that. Today I forgot. All right, any questions before we stop for today, for right now, for the lecture? And when we'll get back together in our lab, what I want to do, and I'll talk about what we're going to be doing in lab, is I want to talk about neighbor references for each tile for lab 5. I want to do a clockwise rounding, top, right, bottom, and left for winding when it comes to how I set up my neighbor references. And then I want to compute the Euclidean distance to the target for each tile in real time. Every time I move my ship or my target, it should recalculate the distance from the cost from the ship to the target. Okay, that's what I want to kind of do. These are the intermediate goals that I want for lab 5. And if we get more done, we'll do more for today. Any questions before we move on and I say goodbye until I see you during lab? Thanks, Lyra. Okay, thanks, Nahar. All right, guys, thank you so much. Again, what we're going to see, the next lab session is at 11 o'clock. Thanks, Sean. We'll go from 11 to 1 with the first lab, and then we'll record the one from 1 to 3. So I'll see everybody during those time frames. Thanks so much, guys. And I will see most of you guys in lab. And if not, I'll see you guys next week. Remember, next week, just before you guys go, remember that assignment 2 is due next week. And you need to sign up for groups in order for you to do it. So please do that. That would be very bad if you didn't, then you can't see your assignment. And then you're going to go, Tom, I don't know why, but I can't see my assignment. It's because you haven't joined a group. So join one today if you haven't done one already. Thanks so much, guys. And I'll see you guys during lab. Thanks.